Hello, everyone. Thanks for joining us here on another Telops webinar. My name is Jean-Philippe Gagnon, and I'm a field application engineer at Telops. So I'll be acting as your host today. And before going into the details of this presentation, let me just get a few housekeeping things out of the way. First, I want to let all of you know that this webinar is, of course, being recorded, and a link to download or view the recording will be sent to all attendees in a follow-up email shortly after the webinar. We also encourage questions from the audience. So if you hear something during today's presentation that sparks your interest or would like to know more or have more information on any of the topics presented today, please feel free to use the GoToWebinar question box. Should be easy to find in your GoToWebinar app. I will reserve a few minutes at the end of the presentation to answer some of the questions you had posted on the app. Just so you know, also all live questions will be answered, if not live, in a follow-up document that will be sent along with the recording of the webinar. All right, so as people are trickling in here, let me just take a few minutes to share a poll question with all of you. This poll question will allow me to get to know you a little bit better, what kind of audience we have here today. So just a simple question. Here it is. You should see it on the screen. So the question is, how would you rate your knowledge of hyperspectral imaging technology, since this is the topic of today's webinar? So either you don't have any direct experience, but interested in the technology, basically you want to know more. No direct experience, but have considered the technology before. You may have direct experience with collecting or processing hyperspectral data, or actually you are a hyperspectral imaging expert, in which case we may invite you to join us on a future webinar with us. All right. Let me look at the audiences. I'll just give a few seconds to give the chance to everybody to answer the questions. All right, and I'll close the question. I'll share the results with you here shortly. Let me yeah. Here are the answers. So most of you have direct experience and have considered the technology and have collected and also post-processed some of the data. So it will be good. As this webinar here today, the topic is how to choose your hyperspectral system. So it's good that some of you already know the basic of it. Hopefully you'll gain some knowledge from today's webinar. And yeah, all right. On that note, let's close this up and dive right into our main presentation. So once again, thank you for joining, and also feel free to ask any questions during the webinar or wait at the end. Like I said, I will reserve a few minutes afterwards to answer questions. All right. A few notes, a few basic information about Telops, who we are. So Telops as a company was founded back in 2000. So celebrating our 25th anniversary this year. We are based in Quebec City in Canada. That's on the eastern side of Canada, so nice and warm today. We have around 90 to 100 employees. Oh, surprised that we don't see the slide. Sorry, I must have hit the wrong button. Here we go, sharing again. Thanks for my colleague to pointing this out to me. Now I guess everybody can see the slides. All right, so yeah, we have around 90 employees here at headquarters, engineers designing the cameras, integrating and testing all of the cameras. We also have offices in the United States and France as well, and also a vast network of distributors worldwide. So Telops, we are established established stuff as a world leader in infrared technology since 2000. We're designing infrared, high-performance infrared cameras, both broadband and multispectral, but also hyperspectral cameras, which will be the topic of today's webinar. In 2023, Telops joined a larger group, a group of different companies, and we took we decided to take the name Exosense. So we're now part of the Exosense family, which we're all very excited about. So head over to our website if you want to know more about the companies who are our sister companies as well. A few history about hyperspectral development at Telops. So our first hyperspectral camera was designed back in 2005 and was called the first. So the first and it's the little blue unit that you see on the lower left corner. Shortly thereafter, we started using or processing the data and came up with our first gas detection program or an algorithm. And this is the image of the little boat that you see at the top. It's supposed to be, a little animation. So we did our first trials back in 2006, releasing gases and detecting and identifying gases and compounds with our first hyperspectral sensor. In 2008, we designed the airborne platform to go along with our hyperspectral sensor, which allowed us to take the system to the sky and use it for the same thing, gas detection, but from an airborne perspective, as well as other applications such as in the mineral and geology sector. In 2010 and 2018, we made various modifications and kept making our gas detection algorithm better and better at detecting and identifying gases, and on top of that, quantifying the emissions. So now we're not only able to detect, identify, but also quantify the emissions. In 2021, we released the newest version of our hyperspectral sensor, we call the HyperCam Airborne Mini, which is a miniaturized version of our first generation sensor. Much smaller, smaller size, weight, and power, which allows the unit to be installed in very small aircraft, drones, or helicopters. And shortly, a year after that, we released a ground-based version of it, which we call the HyperCam Mini XLW. And in 2025, Telops and Exosense acquired LR Tech, a company hyperspectral sensor manufacturer, also based in Quebec City. And our product portfolio increased to incorporate VSR, ASIST, and SPEARS instrument. And I'll talk about those a little bit later. Looking ahead, we've got great development right now at Telops. Again, miniaturizing our sensor, making them always better and better. And we're looking ahead, and or surely will eventually come up with, or it is in design, the HyperCam, which we call the HyperCam Nano. It's a much still miniaturized version of our HyperCam Airborne Mini. So this instrument, still hyperspectral, same technology, smaller package, able to fly on board quadcopter drones. So that's development in a nutshell. Now let's just dig a little bit deeper in our main subject. Oops, sorry, went a little bit ahead. About key characteristics which will allow you to choose the best hyperspectral system for your applications. So in this webinar, we'll focus on 4 main characteristics to compare our products against each other. So those will be imaging capabilities, spectral bandpass, the data rate, and noise characteristics. And we'll compare all of our products from the different families against all of these characteristics. Of course, these 4 characteristics are intertwined with each other. So I'll talk about how they affect each of them. So the first one is imaging capability. So what basically you're trying to answer the question, what are my spatial resolution requirements? Spatial resolution, just as most of you already know, is the ability of an imaging system to resolve very small objects or features. So it's really important that you determine ahead of time how many pixels you want to put on your target pen, which will vary on, of course, the hyperspectral system, the type of optics, but also the distance that you want to operate. So things you want to consider are detector format, basically the number of pixels, total number of pixels on the infrared detector. So this will influence the total field of view, FOV. Also, you want to consider the instantaneous field of view, and by that I mean the field of view of a single pixel. So the size of an area seen by an individual pixel, and this, of course, will depend on distance. And if you multiply the IFOV, or the instantaneous field of view, by the number of pixels, you'll get the total field of view of the system. So here I've put different 2 examples. One obtained from our Hypercam Mini XLW of a methane leak. That's what you see in purple. So you see the great image quality, very detailed imagery that this sensor is capable of producing, along with hyperspectral or the spectral component, which allows us to detect and identify the gaseous emissions. On the other hand, we have images of the spheres instrument looking at a fighter jet and able to measure the properties of the not only the aircraft, but also its jet exhaust, the gases and the exhaust plume. So one of them, Hypercam Airborne, the Hypercam Mini, Hypercam Mini will give you a very detailed image. The spheres, on the other hand, will give you more limited spatial information, but has a lot of other advantages, as we'll see later. So let's compare the different products that we have. On the single pixel side of things, we have the VSR and the Assist. Those are the 2 units that you see here. They feature just 1 pixel. So those are single pixel sensor. Going higher in spatial resolution, we have the spheres that I was just showing you before. So this features an 8x8 cooled infrared detector. So basically all of our hyperspectral sensors are cooled infrared detectors that feature cooled infrared detectors. Sphere features an 8x8 pixel. So it starts to give you a good spatial resolution. And on the other end, we have the Hypercam Mini, the Hypercam Airborne Mini. Those feature infrared detectors featuring 320 by 256 pixels. So a little bit more information on the instantaneous field of view and the field of views of the different sensors. I've put that, I've made this chart here to give you a sense of the different field of views. All of our hyperspectral sensors can be equipped with telescopes to modify the field of views. So it's really up to you to determine the size of the field of view that you need as a function of distance, of course. And then look at this table here to determine the right telescope that you need. And also if you need spatial resolution, go with the spheres or the hypercam. If a single pixel will do the job, and I'll put on examples of different applications in the presentation to give you a sense of what kind of application those sensors can be used. And it's also important to remember that the Hypercam Mini and the spheres, although they feature large focal plane arrays, you can always reduce those focal plane arrays. That is, record less pixels. So those sensors are not fixed to 320 to 56. It's just the maximum size of the array is 320 to 56 or 8 by 8. But you can reduce, crop the window down, record less number of pixels, and this will increase your data rate. And we'll see examples of that later on in the presentation. Again, if your application calls for a telescope that you're not able to, none of our standard offer applies, you can always contact us, and we'll be glad to work with you to design a specific lens or a specific telescope just for that. So that's something that we can always do with all of our equipment. Let's look at a close-up here. Basically looking at the Hyperspectral Mini series. So those are the Hypercam Mini XLW, the Midway Fast was released last year, and the Hypercam Airborne Mini. So those obviously they feature our largest focal plane arrays, 320 by 256, like I just mentioned. They combine high spatial, of course, spectral and temporal resolution. So basically you have the whole package here. So they are based on Fourier transform infrared technology, and that is true for all of our hyperspectral sensors. So they are all based on Fourier transform infrared technology. I won't go, unfortunately, I don't have time in this presentation to go through the detail of how exactly it works on the inside, but we have made in the past several webinars on that topic. So feel free to head over to our website in the resources page. You'll see all the different webinars that we've produced, and feel free to watch them at your leisure, or you can also watch them directly on our YouTube page. And yeah, of course, if you have any questions or want to know more, feel free to reach out to us. So our mini series feature both ground-based, mid-wave, and long-wave detector. So those are great, like I was saying, for imaging gaseous components, like you see multiple examples here, but also work very well in the geology sector, looking at different minerals. A lot of minerals have features in the long wave, for example. Some of our customers use them in the agricultural sector. Look at, for example, ammonia emissions from the air. Ammonia being a big part of, or making up an important kind of part of fertilizer. But yeah, a lot of different applications. And here are the specifications for all of our 3 different instruments in this series. So like I said, they all feature cooled infrared SLS detectors. They all have 320 by 256 pixel array. And you can see the different other specifications here, but the total field of view of these sensors, because they are basically the same platform, they are 14 by 11 degrees. They feature 14 by 11 degree field of view, and this, of course, can be modified by adding telescopes. All right, switching gears here and looking at spectral band, talking about spectral resolution this time. So questions that you might want to ask is, what spectral band do I need? Well, the first criteria would be to kind of understand that infrared radiation, every body or every object above absolute zero will emit some amount of infrared radiation, and the exact amount is governed by the Planck law. So Planck law is just a mathematical formula. that tells us if you know the temperature of an object, then it will tell you the corresponding radiance or power energy, infrared energy that this object will emit. And this is strictly a function of temperature. And as you can see on the graph on the right-hand side, the higher the temperature, the more energy the object will emit. But also, you see the peak emission, the wavelength at which, or the wavelength or the wave number maximum that will emit the maximum amount of energy tends to move towards shorter and shorter wavelength as the temperature increases. So basically, if you want to image low temperature object or atmospheric gases, for example, the long wave would probably be more suited. Whereas if you're interested in looking at very hot gases, such as gas combustions, exhaust or engines, jet exhaust, for example, they have very high temperatures, and so they will emit a lot of energy in the midwave. So a midwave instrument might be better suited for that application. So this is the first kind of criteria that you want to pay attention to. So what temperatures will I be measuring with this type of instrument? The next one is obviously what kind of material am I interested in measuring? For example, gases, minerals, polymers, or inorganic salts, they all have very specific absorption features. And the graph here on the right-hand side illustrates some of them. So you see that different components will have very specific absorption features. So some of them have features in the long wave, some of them only have features in the midwave, or a mix of everything. So it's really important to determine which gases are of interest. And then you can pick either the long wave or the midwave sensor to be able to detect those gases. Same for minerals. Minerals have different signatures also, and they all have individual signatures. So again, it's really important to note where the peak absorption are and select the proper instrument. It's also good to keep in mind that if you're making observations outside or over long distances, the atmosphere in between the camera and your object also contains gases which emit at very specific wave number or wavelengths. So it's important to understand where the spectral band, what's the spectrum of the atmosphere, because you'll be measuring through that atmosphere. So if you're, for example, trying to detect CO2 at a distance, you'll be imaging CO2, atmospheric CO2, and the CO2 that you're trying to detect. So they all compound together. So it's important to realize that. And at Telops, we have a multitude of simulation tools that will that can guide you to estimate the signal that you'll get if you're, for example, thinking of using a mini XLW to measure ammonia through an atmospheric layer, from the air at 1,000 meters. We can take all of these parameters in and compute what will be the estimated signal that you'll get. So it's important to do that because even though for some compounds, like I said, have spectral absorption feature both in the long wave and in the midwave. If you're strictly looking at the theoretical signature of that molecule, for example, here I did plot the signature of methane both in the long wave and midwave. So if you're strictly looking at the theoretical or the measured absorption or spectrum of a single molecule, it may look like in the midwave there's a clear advantage, but if you factor in all of those other parameters, such as the fact that you'll be imaging through the atmosphere, and the methane that you'll be looking at is probably atmospheric temperature, will be in thermal equilibrium with that atmosphere. It turns out that if you do the math, then it turns out that in the long wave, you'll get a greater signal. So yeah, important fact. And also some of those molecules, like hydrocarbons, for example, methane, propane, and methane, they all, in the midwave, they have a very prominent absorption feature, but all of those gases have the same, or the same absorption feature at the same wavelength. So in the midwave, it's very difficult to differentiate between methane, propane, ethane. They all have the same, or they all have their absorption feature at the same wavelength. Whereas in the long wave, they spread out in wave number or in wavelength. So we call that fingerprint. We call this the fingerprint region. So in the long wave, you have the added advantage of being able to differentiate between the different components, something that you cannot necessarily easily do in the middle. So again, another thing to keep in mind while selecting your sensor. So what about the spectral band of our different instruments? Well, you have them there under a nice little image. I've put down the atmospheric transmittance at the background, so you see most of our, or some of our instruments were specifically designed to fit with the atmospheric window. That is the part of the atmosphere where there's the transmittance is the highest. So at the top, we have our Hypercam Mini midwave, so from 3 to 5 micron. We have our Hypercam Mini XLW in the long wave, so 7.8 to 12.4 microns. And we have the Assist, which features, again, I remind you that the Assist is a single pixel instrument, hyperspectral instrument, but has a very wide spectral range, so ranging from 3.5 all the way to 18 microns. And you have the spheres from 2 to 12 micron, and VSR, which is offered in 2 different spectral bandpass. So we have the VSR wide bandpass, so from 2 to 12. VSR ultra wide bandpass from 2 to 15 microns. So of course, those are spanned in a very wide range of detectable gases and minerals. Let's, again, similar to the other portion of the presentation, let's do a close-up on a specific instrument. Here, let's look at the VSR instrument. Again, a single pixel, hyperspectral, still based, like I said, on Fourier transform technology. So this is very fast hyperspectral system, and we'll see data rate a little bit later. But features an ultra large, an ultra wide bandpass. Like I said, so it's great to measure high energy target, aircraft, ground vehicle, camouflage, explosion, signature analysis, like the images I've noted here. Because it is such a wide bandpass, you're able to look at a multitude of gases, and the data rate is tremendous. So it provides close to 100 spectral measurements per second. So it's very fast frame, well adapted to very fast events. And you have the key specifications here of the VSR. We see single pixel detector, spectral range, 2 spectral ranges are offered. The different field of views are noted here also. So based on the different telescopes that you can add to the VSR. So ranges from 6.4 millirad of field of view to almost 19 millirad. So really depends on what type of applications you want to do. And of course, it features very low noise, and I'll come back to that later in the presentation. Yeah, the next, and I've touched on this subject just during the last slide. What about data collection rate? So how many spectral measurements can I make with those instruments? So here it's important to understand that hyperspectral sensors have what we call, or are able to produce spectral information as a function of time, obviously. But this may look, at first, very slow because on the inside, they need to generate a lot of images very fast at different wavelengths, if you want, to give you a total spectral or a total spectrum. So even though the data rate, as you'll see, maybe a few spectral measurements per second, internally the camera is being triggered at very fast frequency, at a very fast frame. So we have a tendency in the hyperspectral sensor world to talk about data cube rate, because if you have an imager like the Hyper 10 Mini, like I'm showing here, it will record a series of images at different wave numbers to produce what we call a data cube. So it's the 3D object for which every pixel contains a spectrum. So you have basically a 2D image, and on the depth or on the z-axis, if you want, you have the spectral content. Also important to note that you want to, because those sensors will have a tendency to will need some time to acquire the spectral content. It is important to make sure that this time, or ideally during this time, the scene should remain fixed or not changing, or changing at a slower pace than the acquisition speed. So this is all to minimize what we call scene change artifacts. The fact that the scene may change during the acquisition of the data cube. So for example, if a data cube takes 1 second, the scene should remain static for that 1 second. If not, then any movement in the scene will create artifacts in your spectral data. Sometimes it isn't too bad. If you're looking at gases, the gas plume may move across the image, across the few pixels during the acquisition time. It may not result in any negative impact, but some of the time, if you're looking at the exhaust of a jet engine, for example, where gases are zooming in very fast across the detector, across your field of view, then it will introduce some movement during the acquisition of the measurement and create negative artifacts. There are some post-processing methods that you can apply to minimize those impacts. And if you want to know more about that, feel free to reach out to me. I'll send you a lot of information. And we have worked and collaborated with different customers of ours in the past to develop such methods. But nevertheless, it's still something that you want to consider during the operation of a hyperspectral system. Like I said also at the beginning, bear in mind that those, for example, the Spears and the Hyper 10 Mini series, they feature a large infrared pixel array, but you can always reduce or crop them down to smaller window, and this will increase the data rate of the sensor. So again, another possibility there. Right, let's look at some data rates. This chart will provide the data rate, or the number of scans per second, or spectral measurement per second, as a function of spectral resolution for the different sensors. So in yellow, you have the BSR, which provide the highest data rate. And like I was saying, it can approach 100 scans per second at a spectral resolution of 16 wave number. This is followed closely by the spheres, which is an 8x8 pixel hyperspectral system. Still, this is a good compromise between speed and acquisition rate. The assist also is right in the middle here, capable of providing more than 10 scans per second at 16 wave number. See on the graph. Down below, you have our mini series. So mini midwave and mini XLW. They are a little bit slower because they provide a lot of spatial resolution. So it's all about compromise when using those instrumentation. So the minis are provide a very high spatial resolution, but we'll necessarily need some time to acquire all of that information. But nevertheless, they are capable of giving you around a few data cubes per second, and even tens of data cubes per second at the coarser spectral resolution. So of course, the coarser the spectral resolution, the higher the speed. The contrary is also true. So if you want fine spectral resolution, then the sensor needs a little bit more time to acquire the information. Again, let's do a close up on one of our instruments. In this case, it's the spheres, which features, as you may remember, a very wide spectral bandpass and also very fast collection speed. So this is really a good compromise between spatial and spectral resolution. It will provide a data cube made up of 8x8 or 64 spectral measurements in the data cube. So again, very good instrument for looking at hot target like jet engines, flares, retrieving spectral emissivity of different materials. So looking at camouflage, coding of different materials, and as well as surveillance and reconnaissance. And you have the main specifications for the spheres. So again, features a cooled SLS detector. So it's basically 3 detectors in one instrument. So a cooled SLS long wave, a mid-wave INSV, and a sphere detector to give you that wide spectral bandpass. 8x8 pixels, different field of views depending on the different telescopes that you may want to couple the instrument with. A few words about noise with these sensors. So noise for our hyperspectral line of instruments are measured in terms of noise equivalent spectral radiance, or NESR for short. So it's basically the noise measurement expressed in radiance units, the same units as the instrument measures. And I've put down a typical NESR plot on the right-hand side here from one of our sensors. So this is a long-wave sensor. It operates from 7.8 to 12.4 microns roughly, so 852 to 1289 wave number. And as you can see, it is bounded on the one end by the cutoff of the detector, and on the other end, the responsiveness of the detector of the detector itself. So it is, the NESR is spectral in nature. So depending on where you look at in the spectrum, the NESR will fluctuate. Of course, it is highest on both ends. Normally, typically, it's pretty flat in the middle, in the main bandpass of the sensor. So you have to remember that NESR varies with wavelengths, but also spectral resolution, observation time, and gain of the detector. So for example, at high, or the NESR will increase if you're working at very fine spectral resolution, and will also decrease if the spectral resolution is coarser. Same thing for observation time. If you give the sensor more time to acquire the signal, you'll reduce the NSR or increase your signal to noise ratio. And a close-up on one of our sensors, basically the last one that we featured. It's called the Assist 2. So it's an atmospheric sounder. It features very low noise. So this was implemented by design because this instrument is dedicated to the study of the atmosphere. It can also do a lot of other stuff, but the main application for this sensor is atmospheric profile. So this sensor looks up at the sky and records measurements on a periodic basis. So every 10 minutes, it takes a reading of the atmospheric column path and is able to determine the characteristics of the atmosphere because it is very sensitive. It is very low noise sensor, which is necessary for this type of application. So it features, like you see at the front, 2 gray canisters. So these are very high sensitivity or very precise black body. So those are reference light sources in the infrared needed to calibrate, to very accurately calibrate the sensor and provide very low noise performance. Basic specifications of the Assist. So this is an instrument that features 2 detectors, so a long wave and a mid-wave detector. Like I said, it's a single pixel. In this case, we don't need spectral resolutions because it's dedicated to the study of the atmosphere. So it measures only one column. Very wide bandpass, 2 to 20 micron, and it's got only one field of view, which is 45 millirad for this application. All right. In the last few slides here, I want to just show you a few applications for these instruments. The first one is using the VSR for smokestack emission monitoring. So this is a group in South Korea that uses the VSR to study or to monitor what's coming out of a smokestack. So what kind of gases are being emitted and in which concentration. So their primary goal is to look at CO2, carbon dioxide, methane, CH4, and nitrous oxide, N2O. So this is all in a goal of understanding those emissions in order to better understand the environmental impact of those emissions. So they've mounted them on top of vehicles, looks like that, for rapid deployment and being able to monitor different sites very rapidly. The other one, like I was talking about just a few slides ago, the Assist 2, capable of or dedicated to the study of atmospheric properties. So it looks up at the sky and measures every 10 minutes, for example, takes a reading of the atmosphere, and then scientists at NOAA, the National Oceanographic and Atmospheric Administration, design a very specific algorithm to retrieve from the measurement from the Assist2 very important properties of the atmosphere. So we're talking about temperature of the atmosphere, the water content, the mixing ratios as a function of altitude. So this is to feed or to better understand the atmosphere, yes, but also try to eliminate the problems of atmospheric balloon sounding. So the way scientists study the atmosphere or retrieve the parameters of the atmosphere to feed it to their atmospheric models is to send on a regular basis atmospheric sounding balloons high up in the atmosphere, which as they go up, they record data. But these balloons, they're not sent every minute. They're just sent maybe a day, every day, or every single day. So, and they're very good at, so the Assist-2 is able to do that, but on a is able to do that every 10 minutes instead of every day or every single day. Of course, there are satellites that does the same job, but the satellites looking down are very precise in the upper part of the atmosphere to extract the parameters of the atmosphere high up, but they're not so precise in determining the parameters of the atmosphere closer to the ground. And so this is where the Assist-2 is able to work. It's very good at determining the characteristics of the atmosphere from the ground, like a few kilometers from the ground. And so it's able to, once they match, the data from the Assist, the weather sounding balloons, and the satellites, then they get a complete picture of the atmosphere, which enables much more precise atmospheric modeling. Last application focus is gas detection, so general gas detection, something that, as you saw from the beginning of the presentation, we did a lot of it at Telops since 2006. So that's using our HyperCam to detect and identify gases. Of course, we have our live, a real-time gas detection analysis software. The screenshot that you see here is able to, in real time, detect and identify up to 15 different gases. So it's very powerful algorithms there. The spectral library is included, so it's basically a point and shoot system. You point it to your scene and you activate the gas detection module, and it will, as soon as something is being detected, it will show up on the screen, color-coded, easily recognizable. And also, it's not only able to detect and identify the compound, it can also quantify the emission, and that's what we see on the right-hand side. So we took our sensor for a little demonstration on the landfill where there was some methane being collected and emitted from a vent from the black pole that you see on the black pipe that you see on the image. So there's methane coming out of it, and that's what we were measuring. As you can see on the three images below the image, the color-coded images. So you see this time sequence with 3 consecutive spectral data cube showing you the concentration of methane in the image. So red is higher concentration and blue is lighter concentration. And if we did look at this vent for some amount of time, for close to a minute, and on the graph below, it plots the amount of methane that was escaping from this vent as a function of time. So very powerful instrument and very powerful algorithms allow you to do this kind of work. Last slide here, key takeaways. I want to summarize on this radar chart the characteristics of the different sensors as a function of imaging capabilities, spectral bandpass, data rate, and noise. As you can see, the VSR in yellow gives you very high spectral bandpass and a very high data rate, but is limited in spatial resolution. Whereas the Mini series, HyperCam Mini Midwave and Mini XLW, are outstanding, feature outstanding spatial resolution, but at the expense of a little bit at data rate and spectral bandpass. Spectral bandpass is a little bit more limited. Good compromise with the Spheres instrument, which provide very high spectral bandpass, very fast data rate, and some imaging capabilities with its 8x8 infrared detector. So I hope this presentation gave you a good overview of our line of hyperspectral sensor here at Telops. Again, if you have any questions, I'll have a look at those. I'd like to remind you also that this presentation was recorded, and every participant will receive a recording of it shortly after this webinar. All right, let's look at the questions. Again, if I know that there's several questions here, I may not have time to go through all of it here in the 5 minutes that I've got left, but be certain that all the questions that you send me will be answered in a document, a follow-up document that will accompany the recording. All right, first questions here. We are interested in the airborne sensor for gas detection and quantification, and we don't have experience in data analysis. Basically, do you offer that service? Yeah, so like I said, we have a gas detection package that works in real time called Reveal DNI. Yeah, this package exists. You can use it. It detects a multitude of gases in real time. You can also work with it in post-processing. So this will provide gas detection, identification, and quantification of the substance. If you're looking for something else, I don't know what your ultimate goal is, but if our standard software does not do that, yes, feel free to reach out to us and we'll discuss what we can do to help. Yes, we'll always work with our clients to make sure that we address their needs, and if we can do something to help you, we'll definitely look at it for sure. Yeah, so feel free to contact me at my email, and we'll discuss this in a little bit more detail. Another question, so is there any significant penetration depth of the minis for geological application? Say we have soil layers over top the geologic units we want to investigate. It would be capturing the signals of the soil. Yes, so yeah, we often have this question. It's a very good question indeed. Yeah, unfortunately, infrared hyperspectral technology can only probe the surface of an object. So it's very difficult to probe beyond that first micrometer of surface. So yeah, if you're interested in something buried underneath, like a topsoil layer, it would be difficult to do that with the direct measurement. But we've made some experiments in the past to detect buried objects, and this was for military applications. The end goal was to see if hyperspectral technology would be able to pick up buried landmines, for example, underneath the soil. And in some configuration, in some instances, it is possible to do this kind of work. Hyperspectral technology can, depending on when the surface was moved around, the properties of the soil changes, and so it's possible to detect soil that was recently moved, or if there's an object hidden underneath the surface, that the properties of the object may change the temperature distribution of that topsoil. So it is possible to sometimes to detect the presence of an object hidden underneath the surface. But if you want to determine the characteristic of the material underneath, hidden behind, underneath a topsoil layer, for example, I'm not sure that would be it. With your imaging devices, how long approximately would it take to do an image with something like 9 to 15 nanometer spectral sampling? Oh yeah, I've presented a chart with data rates with just a few points. But yeah, if you're interested in a very specific configuration, we can chat about that, and I can easily provide exact numbers for a specific instrument configuration. on top of my head there, I don't recall. I can't give you a number, but I'll be sure to do it in the written document that I'll send to it afterwards. What sensor would you recommend for geological inspection of underground mines to detect cracks and fractures? We did some experiments in that application. I think the long wave would be a good sensor for that because the objects are not so warm, room temperature like object. The long wave performs very well, so the sensitivity that you get is high. Also, for underground mines, there are other considerations one has to take into account. One thing that I haven't talked about is thermal contrast. The fact that we need a temperature difference between what we're trying to measure and the environment in its environment for us to be able to make a good measurement. And in the case of gases, we rely on, let's say for airborne measurement, we rely on the fact that the ground is probably hotter than the gas itself, so that provides us with the thermal contrast. In the case of underground mine, if everything is at the same temperature, let's say you're trying to measure a mine face, and the wall is at 22 degrees, and the environment is also at 22, everything is at the same temperature, it is difficult, it is a challenging measurement. But we can also bring in as a light, an infrared source of light, to illuminate that, to give us that temperature contrast, which will enable us to make a valid, good measurement. So it is possible, but there are some other considerations that one has to take into account to do that. All right, on that note, I'm sorry, I don't have time to go through all of the questions, but I hope I was able to answer a good portion of it. Again, I'll provide answers to all of the questions in the written document following that webinar. And in the meantime, if something else comes to mind, just head out to our website. You'll see a place where you can easily contact us and send us questions. And it will be my pleasure to set up a call with you and discuss your application and your needs in greater detail.